Hey everybody, Mr. Rhodey here. Excited for Monday's lesson. We're going to be graphing more rational functions, but really looking at the structure of them as well to help have this go smoother. I also invested some time to make a multiple choice assignment on Schoology just to kind of test you on the concepts overall from this particular lesson. You can retake it as many times as you want until you get the questions correct. It tends to give you feedback and shuffle the answers and shuffle the question order as well. So that should be a new interactive way to do that, as well as our traditional homework worksheet for 29.3. But excited about sharing this with you. This is probably the best thing going forward into pre-calc to retain for the future for rational functions. Okay, if I reference our word wall again, today's lesson is going to be focusing on graphing the rational functions. And if you understand graphing going forwards, eventually you'll be able to write them going backwards from the graphs as well. And obviously we're going to be finding domains, range, x-intercepts, y-intercepts, and identifying those asymptotes as well. So not really the transformations today, more just those critical pieces. Okay, so we're starting on page 453. Again, it's lesson 29-3, finding horizontal and vertical asymptotes. We're going to be able to identify these vertical asymptotes by finding the domain values where they're undefined, and we're going to use degrees of the numerator and denominator of rational functions. So we're going to be relying on our prerequisite skills of factoring from what we did on our last fluency test right before spring break to kind of help us here. So I'm excited to build off of the stuff we've already done. So as you read through this, you'll see it'll mention a few key phrases that we'll add to our word wall later at the end. Discontinuity and removable points of discontinuity. We're also called holes. So we're going to be looking at those asymptotes where it breaks the graph up, but also a new thing called a hole, or something where the graph doesn't exist, but we're going to put an open circle there. The graph kind of skips over that spot. And so as we look at these, they start off right away with example A. We're looking at a rational function where we've got a polynomial on the top and a polynomial on the bottom. We go ahead and factor it to analyze it. We have a difference of squares and our kind of regular factoring on the bottom. You guys are really great at that from the flashcards. We divide out the common factors. So in this case, the x plus 2's and the x plus 2 would divide out to 1. We make note that the x can still not equal negative 2 because that would give me a 0 in the denominator. And that is going to be my removable discontinuity, also known as my hole. There's going to be a hole at x equals negative 2. Okay, looking at the other pieces that are left, I would get 0 on the numerator at x value of 2, so positive 2 will actually be an x-intercept. I would get a value of 0 in the denominator at x value of negative 3, so x equals negative 3 is going to be my vertical asymptote. I can then put all of these onto a graph and be able to see things fully together. So let's go ahead and take a look at try these A and B. You can go ahead and click pause here if you want to factor these on your own, and then check your work against mine, and we'll kind of identify these holes and vertical asymptotes from there. So pause and try them on your own. Okay, so you can see the factoring here. I had a GCF in the top of part A, and on the bottom, something that multiplied to negative 4 but added to 3, positive 4, negative 1. You'll notice I do have some things that divide out here, the x minus 1s and the a's. And over in the b, I had a difference of squares in the bottom. I don't need to do my reversal of the subtraction trick, so these pieces will divide out. And it's really important to make note of what divides out because that's where your hole is going to be. So there's going to be a hole in my first one at x equals 1. We'll show you how to graph those later, but for right now, just appears at whatever value would give me 0 in both the numerator and the denominator. And over here on part B, there would be a hole at x equals 3, because 3 would give me 0 in both the numerator and the denominator. That leaves me with x over x plus 4. So then my vertical asymptote is at x equals negative 4, the value that would give me 0 in just the denominator. And over here, I wind up with 1 over 3 plus x. So my vertical asymptote is at x equals negative 3, the value that would give me 0 in the denominator only. Those values are where my graph breaks, either for an asymptote or a hole, so they are not part of my domain. So the domain, if you will, on this part A would be all real numbers except x cannot equal 1 or negative 4. And so if I'm doing that in interval notation, that's negative infinity up to negative 4. But then again, from negative 4 up to 1, and then again from 1 up to infinity, just removing those two numbers from the number line. And over here, similarly, negative infinity up to negative 3, negative 3 to 3, and 3 to infinity. So again, just can you factor, identify the holes and vertical asymptotes, do that first, and then we'll figure out how do we start to put all that information together into a single graph. Real quick note, they did ask us to use our graphing calculator to investigate these. So again, we were going to have a vertical asymptote at x equals negative 4 on our first one. So we see that here. There's a hole at 1. Okay, so you notice here in the table it says 1 comma undefined. So even though it doesn't look like it, there's an empty space in our graph right there. This also has an x-intercept at 0, 0, also known as a y-intercept. And we'll talk about the horizontal asymptotes here in a bit. The second function it asks us to graph down here had a vertical asymptote at x equals negative 3, as we see there, and it has a hole at positive 3, that undefined piece. So kind of neat to see those. Our goal is how would we graph these by hand if that was our charge, and we're going to be building through that throughout this lesson. And we're continuing on page 454. In this case, in number 2, they're going to give us the factored form already and identify vertical asymptotes and any holes in the graph. So first of all, as I look at this, I notice that the x plus 4 and the x plus 4 are in both the numerator and denominator. So in that case, I am going to get a hole at x equals negative 4. But then I also notice there's another common fact here, a single x and a single x. So that will create a hole at x equals 0, the value that gives me 0 in that expression. Okay, that extra 2 does not change the fact that 2 times 0 would be 0. The other portion down here, I'll go ahead and put that in yellow. There will be a vertical asymptote at that value. So there's a vertical asymptote at x equals positive 6. So very different because that only gives me 0 in the denominator. Okay, and so being able to look at those pieces. And again, if I was to take into account the domain of that particular function here, I have to take out all of those values. So from negative infinity up to negative 4, from negative 4 up to 0, from 0 up to 6, and then from 6 up to infinity. All numbers except for negative 4, 0, and 6. Okay, the next part is determining where our horizontal asymptote. Remember, our horizontal asymptote is simply the number that our function will approach on the ends towards infinity and negative infinity. It could cross it in the middle of the graph. It doesn't often do that. It just might. So just know it doesn't mean it can't cross it. It just means it approaches those numbers at the very end of our graph. It approaches it. We've seen this before in exponential and logarithmic functions, these horizontal asymptotes. Or sorry, exponential functions only, horizontal asymptotes. There are 3 key rules that we'll put on our word wall later for how we determine the horizontal asymptote. As you can see here, we're looking at, it depends on the degrees of the numerator and the denominator, so the top and the bottom. When the degrees are the same, we're going to take the ratio of the leading coefficients. We'll look at that in a moment. When the denominator is larger, the horizontal asymptote is simply y equals 0. And when the numerator degree is larger, there is no horizontal asymptote. No horizontal asymptote. So let's take a look at their examples here. So first of all, looking at our first one here, I'll highlight, this is degree 1 on top, degree 2 on the bottom. The bottom is larger, therefore the horizontal asymptote is y equals 0. In part B, it's degree 1 on top, degree 1 on bottom, so same degree, ratio of the leading coefficients, that is the 2 and the 1. So it's 2 over 1, y equals 2 over 1, or y equals 2 is our horizontal asymptote for part B. Okay. Go ahead and take a look. Do you think with those 3 rules, comparing the numerator and denominator degrees, can you decide what the horizontal asymptotes are for the try these B's? Go ahead and hit pause, see if you can maybe write down your answers, and then you can check them against what I put down next. Okay, ready to check your work? What I have for this one is a degree 1 on top, degree 1 on the bottom. Therefore, the degrees are the same. And so as I consider that, that's going to be the leading coefficient. So in this case, it's a -1 on top. Yes, the leading coefficient is the number that goes with that power of x. And on the bottom, it's a +1. So y equals -1 is my horizontal asymptote for part A. On part B, I have degree 2 on top, degree 1 on bottom, so the top is bigger. Whenever the top degree is bigger, there is no horizontal asymptote. And then on part C, the top degree is 1. This is x to the first. The bottom degree is 2, so the bottom degree is the largest degree of the polynomial. So this horizontal asymptote is y equals 0. You don't have to worry about leading coefficients here when the bottom degree is bigger. That's because if x is some really huge number, that huge number squared is way bigger than that huge number on the numerator. So dividing by a huge number is going to take me to 0. Back in A, when the degree was the same, if I divide by a huge number over a huge number, it's going to approach those coefficients. So that's one of the big reasons we see that difference. Again, these numbers are asymptotes. Generally, you don't cross an asymptote, but you could in the middle. It's just on the ends you don't. But in part 4, it asks me to give the range, assuming that the graphs do not cross the horizontal asymptote. So if that's the case, they don't cross, then I have to just remove that number from my range. So my range here will be all the numbers except for -1. For the red one, since there is no horizontal asymptote, I don't remove anything from the range, so it's all real numbers, or -infinity to infinity. And on this one, of course, I would remove the number 0 from my range. Again, usually you're going to graph to see the picture of it before you give those numbers, and we'll see how that plays out in the later examples here. Okay, so again, number 5 here asks us to determine the degree and leading coefficient of the numerator and denominator and give the equation of the horizontal asymptote. Since this one is factored, this is, if I was to multiply it out, I would get a 2x squared on the top. I won't multiply everything out. And on the bottom, x, I would get x cubed on the bottom. The degree of the bottom is larger, cubed versus squared. Therefore, the horizontal asymptote is at y equals 0. Okay, if the bottom is bigger, it's always y equals 0. So to fully go through this, to graph all these things, we're going to have to simplify it. That's the factoring piece. We're going to identify the vertical asymptotes and holes. If anything divides out, that'll create a hole. Identify the x and y intercepts, much like we did in our last lesson. Plug 0 in for the y-intercept. And for the x-intercepts, we're just looking where the numerator is 0. Identify the horizontal asymptote like we just talked about, and then throw this stuff on a graph. Start plotting points and kind of going from there. So let's take a look at one that they did, and then we'll work one together. They started with this function, x squared plus 5x minus 14 all over x squared minus 4. You can see over here the factoring that they did. Simplifies all down to x plus 7 over x plus 2. You would only need to plug into this simplified function for future y values, for future points. We made note that at x equals 2, because it's in the numerator and denominator, that's where a hole is. The vertical asymptote is what makes 0 in the denominator, so that's just the -2. You see that here in your graph, so vertical asymptote, -2. The hole at x equals 2. You can actually get a value for that. Okay, f of 2. Let's plug it into our now simplified form. That's 2 plus 7 over 2 plus 2. So that's 9/4, or also known as 2.25. So if you notice, this empty hole here on the graph is at 2, 2.25. The x value is 2. And the y value, the output, is 2.25, but it's this empty hole. X-intercept, where does the numerator equal 0? Just at -7. So we see -7, 0 here for our x-intercept. Y-intercept, plug in 0 to this new function, 7/2 or 3.5. That point can be plotted. Horizontal asymptote degrees were the same, therefore leading coefficient 1 over 1. Y equals 1, you see that graphed. And we had our hole in y-intercept that allows us to draw a nice gentle curve. And again, we had our 3.5, our -7, 0 x-intercept. So from there, we could approach the horizontal asymptote and approach the vertical asymptote, putting all those pieces together. If you needed to, you could plug in different values of x to get more points if you wanted to make your graph even more accurate. But again, we're just looking to get those really key asymptotes and intercepts and draw a quick sketch. All right, let's look at one together. Okay, I'm going to walk you through graphing a rational function by factoring it and finding all of these interesting pieces here. So step one, of course, is just to go ahead and factor it. F of x is equal to, we have a difference of squares on top, x plus 2, x minus 2. And again, if you wanted to pause this and try it on your own, I encourage you to. A GCF of x on the bottom, leaving me with x squared minus 3x minus 10. And to factor that part, things that multiply to negative 10, but add to negative 3 is how I'm going to break that apart. 5 and 2 certainly seem interesting. Negative 5, positive 2. So I finally have f of x equaling x plus 2, x minus 2, all over x minus 5, x plus 2. First thing I notice, we do have some common things to divide out, the x plus 2 and the x plus 2. We've seen this before in our simplifying section. This is what's going to create a hole at x equals negative 2. So f of x equals x minus 2 on the top, x minus 5 on the bottom. And now I can use this simpler version as I continue to work. What's the y value of this hole? I have to plug it back in. So f of negative 2 is equal to negative 4 in the numerator, negative 2 times negative 7 in the denominator. So I get negative 4 over positive 14, negative 2 sevenths. So negative 2 sevenths is going to be down here for that hole. So you see I've plotted that already. So I factored, I found my holes. My second step, really that was my second step, was the holes. The third step, of course, is going to be my vertical asymptotes. That's where it's 0 in the denominator. So in this case, it's x equals 0 and x equals 5 are the two values that would create 0 in my for my denominator. So I can draw in a vertical asymptote at x equals 0. You can kind of see that coming in. That also means there'll be no y-intercept here. And then 1, 2, 3, 4, 5, x equals 5. My next step is going to be my horizontal asymptote. Looking at the original, the bottom degree was larger. So that means it's going to be a horizontal asymptote at y equals 0 by definition. My x-intercepts are where the numerator is equal to 0. So in this case, that's x equals positive 2. So 2 comma 0. That's what this numerator tells me. 2 comma 0. So yes, notice this does cross the horizontal asymptote, but it doesn't do it at the ends. It just does it in the middle here. 6, my y-intercept, f of 0. If I plug in 0, I get negative 2 over 0 times negative 5. I can't divide by 0, so there's no y-intercept, no y-intercept, because again, I'm not going to cross that x vertical asymptote there. So again, how do I start to graph this? You could just plug some numbers into what you have left here. So you've got this f of x equaling x minus 2 over x minus 5, and just plug some random numbers in to start to kind of piece it together. So for example here, on this very left-hand side, I know it's going to be approaching this vertical asymptote and going down, and approaching this horizontal asymptote as it goes to the end. Between the two vertical asymptotes, I already have 1 point at 2, 0, so I'm going to plug in 1. What's f of 1? That's going to be negative 1 on top and 1 times negative 4 on the bottom, or positive 1/4. So at 1, it's at 1/4, right around there. So that tells me it's probably going up as it approaches this vertical asymptote. I already have 2. I'm going to plug in 3 or 4. I'll go ahead and plug in 4 just to see where that point is. F of 4. 4 minus 2 is 2. 4 minus 5 is negative 1. So I get negative 1/2. So at 4, it's at negative 1/2 over here. So again, it's going down, and then it's going to approach that vertical asymptote and start going down. Where is it? At 1, 2, 3, 4, 5. I probably should plug in 6 to get a point. F of 6 is going to be 4 on the numerator, and then 6 times 1 in the bottom, so that's 2/3. So 6 comma 2/3 is right around here. I know it's got to approach the vertical asymptote going up and approach the horizontal asymptote going to the right. So pretty neat. It's kind of like got this cubic thing going on in the middle. Um, and I can start to kind of identify all these really kind of neat things. So let's go ahead and talk about domain and range here. So domain is all the numbers for x that it does not cover. So in this case, my domain is going to be from negative infinity up to that -2 where there's the hole, and then from -2 up to 0, because I got to take out that vertical asymptote. Again, from 0 to 5, because there's another vertical asymptote there, and then again from 5 to infinity. So all real numbers except for -2, 0, and 5. And then my range here, which is kind of interesting, my range actually happens to be all real numbers because I wind up going up for infinity, down for an infinity. I actually cross that horizontal asymptote. That won't always happen, but in this case, it does. So my range just from the graph, all the y values, negative infinity to infinity. So yes, there was a lot there, but gonna go through those steps one by one when you're working the homework. Check your keys. Factor first, find the holes, find the vertical asymptotes, plot those, find the horizontal asymptote, plot those, find the x-intercepts and y-intercepts, and then using your simplified version, plot a few points. It's kind of like the brute force method to just kind of get a sense of it. You can always then use Desmos or your graphing calculator. Make sure to put the numerator in parentheses and the denominator in parentheses to verify what your picture looks like. Okay, I'll be around, I think, multiple times and offer a couple of different Zoom drop-in help sessions. So hopefully that'll be helpful to you. But keep practicing this. It'll take some time. But the key point is we're simplifying like we did back in FT5. But now that we've simplified, we know what it creates. It creates holes, creates vertical asymptotes, it creates x-intercepts. And horizontal asymptotes is just looking at those degrees as well. So next thing you want to do is look at your word wall, copy down a summary of what we learned today, and then we're going to try and apply it on the homework. Okay, here's our overall word wall. I'm going to go ahead and scroll up. We have the parent function, 1 over x, that we moved. Now we're looking more so at this idea of a rational function with a polynomial on top and a polynomial on bottom that we have to factor. You know, there could be these leading numbers here, leading coefficients. But in reality, we want to look at rational functions in factored form. You can pause to take this down on your word wall if you want, or right off to the side as you get ready to try the homework. But the main key points are you find the y-intercepts by evaluating, by putting 0 in for x, f of 0. The x-intercepts are the values that make just the numerator 0. The vertical asymptotes are the values that make just the denominator equal to 0. The holes were the things that make both the numerator and denominator 0, or the factors that divide it out. So if you're able to divide those out, you might actually find the holes first before finding the x-intercepts and y-intercepts and vertical asymptotes. And then the horizontal asymptote was all about just comparing the degrees of the top and the bottom. If the degree of the top is bigger, no horizontal asymptote. Degree of the numerator bigger. If the degree of the numerator is smaller, so the bottom degree is bigger, it's going to be at y equals 0. It's going to approach 0. If the degrees are the same, that's where you have to look at those leading coefficients, a over b. Hopefully that's a good summary of where this stuff is at. This is probably the most important stuff that we'll look at again and probably assess on next week. And again, I'll carry you over into pre-calculus again next year. Again, feel free to stop by during the Zoom drop-in help sessions. And don't forget about the multiple choice Schoology assignment, just to kind of, you can keep retaking it as many times as you can until you get 100% to really drive forward. When does it create vertical asymptotes? When does it create holes? When does it create a horizontal asymptote and x-intercepts?